Okay, guys, we were asked about 2017 free response question number 4. This was a tough problem here, everybody, no doubt about it. All right, so in this particular problem here, and remember this is a non-calculator question if it was number 4 here, they're telling you that at time t equals 0, a boiled potato is taken out of a pot on the stove and left to cool. They tell you what feels like an initial condition right here. The internal temp of the potato is 91 degrees Celsius at a time of t equals 0. This is an odd piece of information that they gave you right here. The internal temperature of the potato is greater than 27 degrees Celsius for all times greater than 0. My quick interpretation of that, and we're talking about Celsius here, and who the hell knows what any of that stuff means, but my guess would be that 27 degrees might be room temperature in Celsius right here, and it would stand to reason then that if you took a hot potato out of boiling water, of course water boils at 100 degrees Celsius, so that 91 right there seems realistic for an initial temperature. The potato is never going to get colder than the surrounding room temperature, so I'm thinking that's what's relevant here, but I'm not sure that that's important. Okay. They've given us a function right here, a function h, that's going to tell us the internal temp of the potato. And then in addition to all that, they've given you the derivative of h taken with respect to time there. And they're telling you here that h of t is measured in degrees Celsius. And here again is that same little initial condition. So it was a little bit odd right there, guys, that they actually gave you that piece of information twice. Not entirely sure why. So let's take a look at part A here, guys. We're supposed to write an equation now for the line tangent to the graph of h at t is equal to 0. That's part 1. And then use that equation to approximate the internal temp of the potato at t equals 3. Okay, so the first thing they wanted was the equation of a tangent line. Well, the first thing we need to know in order to come up with the equation of a tangent line is our point of tangency, and they were kind enough to give us that right over here, guys. We know that when t is equal to 0, our h, our temperature, I guess that stands for heat, is 91. So that right there is the point of tangency. The other thing we need, though, is the slope of the tangent. And the slope of the tangent, hopefully we understand this one right here, comes from evaluating our derivative right here. So that is going to be the derivative of h taken with respect to t, but they said to evaluate this at the time right here when, let's see, use the equation of the tangent at the time when t was equal to 0. Well, the interesting thing here is that the derivative that they gave us doesn't use t as an input value, it uses h. But this initial condition right over here tells us that when your time is equal to 0, the h value you're dealing with is 91. So we're going to evaluate this derivative when h is equal to 91 degrees. Okay, so we're going to take that derivative right there, which is a negative 1/4, and take this here times a 91 for h minus a value of 27. Okay, non-calculator question here, guys. So this is a negative 1/4 times, and a 91 minus 27 is going to get us a 64 degree temperature there. That makes me feel pretty good because that negative 64 here, everybody, is evenly divisible by the 4 on the bottom, and that is going to get us a negative 16 there for the slope of our tangent. Now, if we're trying to interpret that in the context of the problem itself, h is temperature, t is time. So what we're dealing with, and I wouldn't write this down on your paper, guys, is negative 16 degrees Celsius right here divided by, we were talking about minutes, I believe, for our unit of time right here. Let's see, where does it actually say that right? Yeah, there it was. I crossed it out. Time, t, in minutes. So that means, everybody, that the potato is losing about 16 degrees Celsius per minute at that time. Seems kind of quick to me, but okay, we'll run with that. So now, everybody, we knew our point of tangency right over here, and we know that our slope of our tangent is negative 16. So for the equation of the tangent line, here we go. Instead of a y, we're using h right here is what it is that we're measuring. So we are going to go with an h, and then it would have been minus your y-coordinate right here, or your h-coordinate, so an h minus 91 is going to equal the slope of your tangent, which was a negative 16, and multiplied by, normally this would be an x, but in this case your independent variable is going to be a t, and then minus the t-coordinate, which is going to be 0. So that's one form of the equation. It would probably be a little bit easier to write this thing now as h is equal to, and that would be a negative 16t and a plus 91. Okay, so that's the first part of what they were looking for right here, guys, which was the equation of our tangent line. So because that's an answer to a question that they asked, I'm going to go ahead and box it up. But they also say use this equation to approximate the internal temp of the potato at a different time value. Remember that the equation we just came up with is only going to give us an accurate value of h only at this one value right here of 0. Anywhere else, we're going to get an approximation. That's all it is. So if we want to come up with an approximation right here for h of 3, we're going to go ahead and plug a 3 into this function right here. So a negative 16 times 3 minutes and plus 91. Okay, the negative 16 times 3 is going to be a negative 48. We're going to add that to a 91 right here, and I am pretty darn sure that that is going to get us 43 degrees Celsius for the temperature of the potato then at t equals 3 minutes. So again, that's an approximation, but that is what they were looking for. Let me go back and double check the question again, and I think that's what we came up with right there. Okay, that's a wrap then for part A. Let's take a look at B right here. They want us to use the second derivative now, d2h dt2, to determine whether that answer in part A was an underestimate or an overestimate of the real internal temp of the potato at t equals 3. So okay, they kind of gave us a hint right there. Let's go ahead and let's start working on finding our second derivative. So to do that, let me write down again what we already have on the previous page right here. The dh dt was a negative 1/4 times a value of h minus, and I believe that was a 27. Let me go back and double check that right there. Yeah, that was correct. All right, so now we're going to do our second derivative. The second derivative of h taken with respect to t here is going to equal, okay, and we just need to take the derivative of this function that we came up with here just a second ago. But the important thing to remember is that we're differentiating with respect to t. This derivative, though, was written with in terms of h. So this is going to be implicit differentiation here, everybody. Okay, if we thought about what this would be, you could rewrite this original derivative by distributing that negative 1/4 as just a negative 1/4 times h and a plus 27 over 4. So when we went to go take the derivative of what is really a linear function, the derivative of that is just going to be the coefficient of that linear function, negative 1/4. But remember, guys, that because we're differentiating with respect to t, we now need to multiply that by dh dt because of the chain rule. Okay, interesting. So that's a negative 1/4 times the original derivative dh dt, which was negative 1/4 times the quantity of h minus 27. And that is going to take a little bit of simplifying, although not too bad right here. The negative 1/4 times the negative 1/4 is going to be a positive 1/16 times the quantity right here of an h minus 27. Okay, so that's our second derivative right there. And what we're going to use that second derivative for here, guys, is to try to talk about the concavity of this graph here at this particular moment in time. And I wonder if this isn't the spot here, which is the reason why they told us that the value, the internal temperature, H, is always going to be greater than 27 degrees. If H is always bigger than 27, then we know that this quantity right here, our second derivative, always has to be greater than 0 here for all values of t. Okay, so what that tells us now, everybody, is that if our second derivative is positive, we know that the curve we are dealing with right here is concave upward. Now, what it is that we are really dealing with right here, guys, is a question about the temperature of the potato right here. And they wanted to know if our approximation in the first part was an overestimate or an underestimate. Well, as I think we can figure out, and actually here's another thing I just thought of, since we know that H is always greater than or equal to 27, in the first derivative right here, we know that our first derivative is always going to have to be negative, but then we just figured that our second derivative would always have to be positive. So that means, everybody, that the temperature of this potato, because the first derivative is a strictly negative function, this function always has to decrease, which again makes sense. You take a hot potato out of the oven, you leave it out at room temperature, the temperature's not going to go up, it's only going to continue to fall. But the fact that the second derivative here is positive tells us that this thing is going to be concave upward. So we're looking for a function that starts high, right up here at 91 degrees, and is always decreasing, but is concave upward. And so that would mean, everybody, that our temperature function is probably going to look something like this, a function that's decreasing and concave upward. Now, what we had done just a moment ago is we had tried to come up with an approximation for the temperature of this function at a spot right over here where t is equal to 3. And the way that we did that was by drawing a tangent line approximation to the original curve, and I don't think I drew this terribly accurately, but okay, this is what we just came up with right here in part A. And boy, actually this is a really crappy graph now that I look at it, but the value that we came up with in part A, which was 43 degrees, is actually the value, the y-coordinate, of the tangent line at this spot right over here when t was equal to 3. So that's your 43 degree mark right there from the tangent line. But the true value of the temperature of the potato at 3 minutes comes right over here. And now I think we can see pretty clearly that because that curve was concave upward right here, we know that the real value of h of 3, actually I should not have written that right there, the real value of h of 3 is right over here next to that. There we go. We'll shrink that down a little bit. And we can see that the real value of h of 3 has to be greater than that 43 degree estimate that we came up with in part A. So let me go back and read the question again here. Use that value to determine whether your answer in part A was an overestimate or an underestimate right there. Okay, so going back to it, it looks like our approximation right here was going to be an underestimate. And did they want an explanation? They actually didn't ask for a justification or an explanation at all, so we can say right here that our answer for part A was an underestimate. And guys, the great thing to realize right there, if they don't ask you to justify or explain, shut up and move on to the next problem. Don't risk saying something that's wrong. Okay, so that's a wrap on part B. And let's go back and see if we can't figure out what's happening here on C. Okay, and in this problem right here, let's read this one right here. For t less than 10 minutes, we've been given an alternate model for the internal temperature of the potato, and we've got this diffie-q that's given to us for that one. So dg dt, sorry guys, I better take a second and write this down right here. The derivative of g taken with respect to t is equal to, all right, the opposite of g minus 27 to the 2/3 power. G minus 27 to the 2/3 power. Ugly, but there it is. Okay, and again, g of t is still measured in degrees Celsius. Oh, and they've given us the same initial condition right here that g of 0 is still going to equal 91. That's maybe not surprising since that's a temperature we knew at the start of this little experiment. So, okay. There's an initial condition given to us. Okay, they want a couple of things right here. First of all, they want an expression for g of t. All right, so given a derivative right here, we're going to try to solve this differential equation and try to figure out what g of t is equal to. All right, so in that case, I'm going to treat this like a normal initial value problem right here. And first thing we're going to do is we're going to separate our variables. I'd take this quantity of g minus 27 to the 2/3 and I'd bring it to the other side. You would divide both sides by g minus 27 to the 2/3, or we could rewrite that here as a g minus 27 to the negative 2/3 power. That's going to get multiplied now by the dg. That is equal to, the negative stayed put. I didn't move that at all. So that's going to be a -1, and then we're going to put a dt there on the right. And now that we've separated our variables, we're going to do an integral on the left and an integral on the right, and let's see what we can do in terms of anti-differentiation. Okay, on this left side right here, we've got a base to the negative 2/3 power. So the antiderivative of that is going to raise the exponent by 1. So we're going to have a g minus 27 now taken to the 1/3 power. We're going to divide by that new exponent of 1/3, which is going to put a 3 out in front. The derivative within is just 1, so we don't need to worry about anything there. That is going to equal, this left side is now going to become the opposite of t and we'll put a plus C at the end of that. And if this was just a regular diffie-q, we would leave the plus C there, but this is an initial value problem because we were given that initial condition. So we now know that when t is equal to 0, g is going to be 91. So let's see what we can do here to solve for C. All right, we're going to get 3 times the quantity of a 91 minus a 27 to the 1/3. We're going to find out in a real hurry here whether we're doing this one right or not. The opposite of t, that's still going to be a 0 plus C. And what I meant by that, guys, is to realize that this is a non-calculator question. And if they want us to take something to the 1/3 power, this quantity here had better end up being a perfect cube, or we're kind of screwed. Or at least we're going to end up with a really ugly answer. Well, sure enough, everybody, in the cosmic way that things always tend to work out nicely, the 91 minus the 27 is going to give us a 64 right here to the 1/3 power is equal to C. And let's go with that. The cube root of 64 is going to be 4. Multiplied by the 3 tells us that C is equal to 12. Probably shouldn't have boxed that up because we're certainly not done with this problem, but let's keep going with that and see where we are now. Okay, so subbing that in, we've got 3 times a g minus 27 to the 1/3 power. That is going to equal a negative t plus 12. And we still have some work to do here, everybody, as we are looking at this trying to get g by itself. So I'm going to copy that. Let's add a new page right here. We'll start back over on the top. And let's see what we can do now to get the g by itself. First thing we're going to do is divide both sides by 3. So let me rewrite this now as a g minus 27, still to the 1/3 power. And on that right side, there's a couple of different ways to do it. Boy, it's tempting. Because that 12 is divisible by 3, I'm going to make that a negative 1/3 t and then a plus 4. If you had left that just as maybe negative t plus 12 all over 3, that would be perfectly fine as well. Remember here, you don't actually have to simplify your answer, so either one of those would have been right. But I'm going to ignore that for right now. We're going to get rid of the 1/3 by cubing both sides, and then we're going to add a 27 to it. So what I think we're going to get then is that g, written as a function of t, is going to be the quantity of a negative 1/3 t plus 4. All of that is going to get cubed, and then we were going to add a 27 at the end of that. Whew, that is kind of a mess. All right, so let's go back to the original question right here. Find an expression for g of t, and that is what we have just done. So that is part of our answer right there, but it looked like there was another question as well. Based on this model, what's the internal temp of the potato at t equals 3? So now we're going to come up here with the value of g of 3, and let's again hope that this one works out pretty well here. Now you'll notice we've already come up with an approximation for h of 3, which we did way back here in part A and came up with 43 degrees, and we knew that that was an underestimate. I'm curious to see if this answer is anywhere close to that. So this is going to be a negative 1/3 multiplied by your t value of 3, that's a horrible 3, plus 4, close it, cube it, and add 27 to it. So where are we, guys? All of that is a negative 1, plus 4 is 3, 3 cubed is, nope, 3 cubed is 27, and adding the other 27 to that, I think that's just a coincidence that those numbers ended up being exactly the same. We get 54 degrees now for the temperature of that potato. Again, we don't know if that answer is right or not, but the 43 was the estimate we came up with before, and we knew that it was an underestimate. So I think saying here that the temperature of the potato now at this spot here was 54 degrees seems realistic to me. All right, guys, so that was a long, difficult problem right there, but I think we've covered everything that they wanted there.